Swayam Prabha. Digital India. Educated India.
Hello students, today we are going to discuss the conditions of spontaneity and equilibrium when a system undergoes a change in state, and we are going to show that one can use energy functions or thermodynamic potentials to obtain a general condition for spontaneity and equilibrium in thermodynamics. So we have already seen that entropy is maximized for an equilibrium state in an isolated system. So if I write it down mathematically, I can say if it is an isolated system, the first law of thermodynamics tells me that it has a fixed value of internal energy. And let me say that for this isolated system, I am going to define its equilibrium state by giving a specific value of its internal energy and the volume of the system. Therefore, the entropy of this system is going to be a function of U and V. Therefore, at equilibrium, I can say that these two derivatives should meet certain criteria. First of all, if I keep U as constant and look at the partial derivative del S del V, this must be equal to 0 because the system is at equilibrium. And then since it is a maximum, the second derivative, second order derivative, del square S del V square must be less than 0. This is what we understand from differential calculus. Now the question is, if I have allowed my system to evolve to an equilibrium state and the system has acquired a finite maximum value of entropy under the given experimental setup, now what would happen to the internal energy? So once the value of entropy is a maximum value under the given experimental condition, what would happen to internal energy? So this means that if I have a system at this isolated system at equilibrium, it is characterized by a constant maximum value of the entropy. Under such condition, if I want to find out these two partial derivatives and I can evaluate them, they will tell me what would happen to internal energy when entropy is a maximum. So basically then we can go ahead and express U as a function of S and V, where now in this isolated system at equilibrium I am using the constant maximum value of entropy and the volume to define its initial equilibrium state. And I can use the cyclic chain rule and write this expression, from where I find that del U del Vs is actually related to two other partial derivatives. But the combination of first law and the second law of thermodynamics for a reversible process condition tell me that I can identify T as del U del SV. So if I put it back, I understand that this first order partial derivative that is related to minus T into del S del VU. Now when the system has already attained the final equilibrium state, S is a maximum and therefore del S del VU must be equal to 0. And since this term vanishes, I will immediately conclude that under such condition del U del Vs should also be equal to 0. So this means that as this isolated system equilibrates in a new equilibrium state, as the entropy attains a maximum, the internal energy also attains an extremum. Then the question is, what is the nature of this extremum with respect to u? Now, this is something of a mathematical exercise which the beginning learners and those who do not like mathematics can skip. But I will just browse through the kind of steps that you need to take to understand the sign of this second order partial derivative that will tell you about the nature of the extremum of u. And here you will see that you need to define this quantity x, which is nothing but del S del VU. Then you can very easily find out what is dx, and you can also find out this del x del Vs in terms of other quantities that you are going to work with. Please note that at equilibrium, the value of x is going to be equal to 0 because we have already shown that the first order partial derivative is of entropy with respect to volume, keeping u constant, is equal to 0. Now, with this, what you can do is you can indeed go ahead, do a little bit of mathematics and show that under the condition of equilibrium, the second order derivative is given by minus t into del square s del v square u at equilibrium. Now, you understand that this quantity, that is the second order partial derivative of s with respect to v, that is less than 0, simply because at equilibrium s exhibits a finite, a maximum value, and therefore the negative sign of this term and the negative sign here, they combine to give the fact that del square u del v square s would be greater than 0. So, what would be our conclusion from here? If in an isolated system, the condition of equilibrium is given by the maximization of entropy, then these two relationships must be satisfied. And then this also means that at equilibrium, when the system exhibits a maximum with respect to S, it also exhibits, for the same equilibrium state, a minimum with respect to U. Now, let us review the condition of spontaneity and equilibrium in an isolated system here. So, if I have an isolated system and if I induce it to undergo a change in state, it will undergo a spontaneous change in state in the direction that increases entropy or equivalently that decreases its internal energy. If I induce the system to undergo a change in state in a direction which is associated with a decrease in entropy or an increase in the internal energy, you would say that this process is non-spontaneous. But if the system has undergone a spontaneous change in state and then reached a maximum value of entropy, then I would say that a new equilibrium state is reached. And at this new equilibrium state, as entropy has reached a maximum value, the internal energy has reached a minimum value. Now, but of course, if you are talking about real systems, they are not isolated at all. So, is this the end of the story? Of course not, because thermodynamics is a theory that has been framed, that has been formulated for application to realistic systems. And this is exactly what is done while we look for a common condition to define the condition of spontaneity and equilibrium in both isolated and non-isolated systems. So in the next few minutes, let's go exploring and see how we can do so in terms of what are known as the different energy functions in thermodynamics, which have been given many different names. We will club them under one single term. We'll call them thermodynamic potentials. So what is a thermodynamic potential? So thermodynamic potential is some kind of an energy function of the system. So this is a state function. So if the equilibrium state of a closed system is given in terms of two independent variables, x1 and x2, its thermodynamic potential, which I use a generic representation here as big epsilon, that is going to be a function of x1 and x2. In that case, I will have d of big epsilon. This is an exact differential, and this must be expressed as functions of the dx1 and dx2, and it must satisfy a relationship like this. Now, we have seen one such energy function already from the first law of thermodynamics. So we label this as the thermodynamic potential of an isolated system. The fundamental equation here is that for a given isolated system at equilibrium, the system is characterized by a given value of entropy, volume and number of particles, and therefore I can say that these are the two variables x1 and x2, and u is going to be a function of these values s and v. Since I have an isolated system, dn is equal to 0, and therefore if I induce the system to undergo a change in state whereby s changes to s plus ds and v changes to v plus dv, what would be the consequent change in u? Du, by the combination of the first law and the second law of thermodynamics, is given by Tds minus Pdv. Here I understand that we identify the absolute temperature T as the partial derivative of u with respect to S, keeping V and N constant, and negative of pressure is the partial derivative of u with respect to volume, as keeping S and N constant. And we can understand that here I can vary internal energy directly by varying the entropy and volume. This conclusion follows from this particular equation. It says that if I use S and V as my independent variables, S is a dependent variable, and then U directly can be varied by varying ds and dv. Now, keeping this in mind, there are several other forms of energy in closed system that we come across in thermodynamics. The first one is enthalpy, where enthalpy is defined as U plus P into V. Since U is a state function, pressure and volume are also state functions. Therefore, I understand enthalpy is also a state function. We have already discussed that. And now I can show that dH is equal to TdS plus VdP. So what I am going to do here is I understand that from definition dH is equal to du plus PdV plus VdP. But if I look into the combination of the first law and the second law of thermodynamics, I understand that du plus PdV is nothing but TdS. So this is what I have put in here. Similarly, this tells us that dH depends on ds and dP. Therefore, I can say that if the equilibrium state of my system is defined in terms of S, P and N, then H will directly depend on the variation of S and P in a closed system. We have another form of energy which is known as the Helmholtz free energy, and it is defined as F is equal to U minus Ts. So in this case, can I write down what is dF? So dF is going to be equal to du minus Tds minus sdt. Now, if I use the combination of first law and the second law of thermodynamics again, what is du minus Tds? That must be equal to minus Pdv. So, I am going to replace these two terms by minus Pdv, and then I have minus sdt. So, I can write down dF is equal to minus sdt minus Pdv. Now, following the definition of an exact differential, I understand that dF is now expressed as something into dt plus something into dV. And therefore, I can say that the variation of F depends directly on T and V. Therefore, under the situation where I am defining the equilibrium state of the system in terms of giving a specific value of temperature and volume, I can directly express F as a function of that temperature and volume in the closed system. Now think about Gibbs free energy. By definition, this is given by U minus Ts plus Pv. So what is dg? If I write this down, then I can find dg is equal to du minus sdt minus tds plus pdv plus vdp. Now I am going to collect these terms. Du minus tds plus pdv. As you see, du minus tds plus pdv from this expression, this must be equal to 0, and therefore I would write that this is equal to minus sdt plus vdp. Now what I find here is then g directly, the variation of g dg depends directly on dt and dp. Therefore, if I specify the equilibrium state of a system in terms of the temperature pressure, then I can directly look at the change in Gibbs free energy as a function of dt and dp. So let us have a look at the different thermodynamic potentials or the energy functions that we have come across so far in thermodynamics. So if we had an isolated system, the equilibrium state could be defined by specifying the entropy, volume and the number of particles, and the corresponding thermodynamic potential would be a function of these three variables. And I define as the thermodynamic potential that energy function whose variation depends directly on the given set of independent thermodynamic parameters with which you are defining the thermodynamic state. Here, I call U as the thermodynamic potential in an isolated system, simply because by the combination of the first and the second law of thermodynamics, I find du depends on ds and dv. Therefore, u depends on s and v. U is the energy function that depends on s and v, and I can use a given value of s and a given value of v for a closed system that is actually isolated. Therefore, I will call U as the thermodynamic potential corresponding to an isolated system. Now, if I have a system in equilibrium with a thermostat, then experimentally How do you define the equilibrium state of the system? You define it by specifying T, V, and N. Now, I have come across another energy function F, which is defined as this, and I find that the combination of the first and the second law of thermodynamics tells me that dF depends on dt and dV. And therefore, I would say that F as a function of tvn defines the thermodynamic potential for a system which is connected to a thermostat and is being maintained at a given temperature, volume, and the number of particles. Now, if you go ahead and have a look at a system which is otherwise isolated but is connected to a barostat. So, in that case, following the same logic, I would be able to define the equilibrium state of the system in terms of entropy, pressure, and the number of particles. And then I find that there is an energy function H such that dH is equal to dependent on directly on ds and dp. Therefore, when I am defining the equilibrium state of the system like this, the corresponding thermodynamic potential is H, or enthalpy of the system. And finally, when I have a system connected to a thermostat and a barostat, then how do I define the equilibrium state of this system? I do so by specifying the temperature, pressure, and the number of particles present in the system. In this case, I identify an energy function G such that dG depends directly on dt and dP. So, I say that under such condition, the thermodynamic potential whose change depends directly on dt and dP is G, and G as a function of Tp and N is the thermodynamic potential in this particular experimental condition. So, once I have understood that there are some energy function associated with a system when it is present in a non-isolated condition, that is, it is interacting to its surrounding by being in equilibrium, thermal equilibrium with a thermostat, or a mechanical equilibrium with a barostat, or in thermal and mechanical equilibrium with both a thermostat and a barostat, there is a common quantity that I could identify in all of them. I identified the way I am going to define the equilibrium state in each system, and I found that in each case I can find an energy function which can be defined as the thermodynamic potential that directly depends on the parameters that I am going to vary in order to carry out a change in state under that experimental condition. Now, if I go back and use these two results that we have already got, then by the combination of first law and the second law of thermodynamics, we can always say that TdS is always greater than or equal to du minus dw. Now, if I consider an isothermal process where there is only pressure, volume, work, I can do the following. I can say that du, from this side I bring it to the left hand side. From this right hand side in this equation, I am taking it to this side. So, minus du plus tds would be greater than or equal to minus dw. Now, since I have an isothermal process, I can take this constant temperature inside this differential and rewrite the left hand side as minus d of u minus ts, that is greater than or equal to minus dw. Now, I know already that I can define the Helmholtz free energy as F, which is U minus Ts. So my conclusion is that if I have an isothermal process where there is a decrease in Helmholtz free energy, that must be greater than or equal to the amount of work done by the system or on the system depending on the sign of dW. Now, if I am carrying out this isothermal process at constant volume, in that case, what will happen? dW would be equal to 0. So, in that case, I would say that for this process, for an isothermal process where dW is equal to 0, dF must be greater than or equal to 0. So, what we are trying to say here is when the system is maintaining a thermal equilibrium and passing from an initial equilibrium state to a final equilibrium state, it will spontaneously do so in the direction where minus dFTV is greater than 0, which means that a spontaneous change in state will be associated with a net decrease in the Helmholtz free energy. So let me take this example and explain. So let me say that I have created the initial equilibrium state here. Here my system is a reaction vessel which is shown here by this white box. This white box is surrounded by a diathermal wall, and it has been placed in contact with a thermal reservoir with which it can exchange thermal energy. But within the reaction vessel, I have placed a separator such that the reactant, blue reactant and the pink reactants, they do not mix each other. They are put on two sides of this reaction vessel. Now, if I want to induce the system to undergo a change in state, then I will withdraw this separator. Now, what will happen? The system is now out of equilibrium. It will now evolve towards a new equilibrium state. Here, the spontaneous direction of change would be where the blue reactants and the pink reactants react with each other, and they are reacting within the reaction vessel for which the total volume is constant. So, when the new final equilibrium state is reached, you will have some equilibrium composition of the system. So, you will have some products and some of the unreacted reactants present in the medium. So, here this passage of this initial equilibrium state to this final equilibrium state is what I would say is isothermal isochoric process. So, you might argue that initially the volume of the system was not the same that was available to the blue reactant or the pink reactant. All I would say is if I look at the initial and the final equilibrium state, the quantity that remains constant is the total volume of the reaction vessel. Initially, V1 was available to blue reactant and V2 was available to the pink reactant, and they were restricted by the presence of this separator. So again and again, I am trying to convince you that in thermodynamics, when you carry out a reaction, you prepare the initial equilibrium state with some kind of a constraint, and then you withdraw that constraint and induce the system to undergo a change in state. Now, when the system has attained a final equilibrium state, then you talk about the comparison of this initial equilibrium state and the final equilibrium state without the internal constraint. And the process that you see here is the withdrawal, has been induced by the withdrawal of the constraint. So in this case, I would say that if the system passes from this initial equilibrium state to this final equilibrium state, the direction of spontaneous change in state is the reaction. In that case, this reaction, if it occurs with the lowering of Helmholtz free energy at constant temperature, at a constant volume of the reaction vessel, then the system will have a spontaneous reaction. And when will the reaction cease? When the chemical equilibrium is established. And that is the condition, that is where the reaction, the free energy under the given condition would have reached an equilibrium state. So this is where I will stop and leave you to ponder about the results that I have shown to you. I have shown to you one non-isolated system where I am carrying out a process under isothermal condition. And in this case, I have carried out this process under not only isothermal but also isochoric condition, and there was no pressure volume work involved. And I saw that the process underwent a change in state spontaneously in some direction, where the process happened at the cost of lowering of the Helmholtz free energy. In my next lecture, we will go back and see how this concept can be extended to the situations where both the temperature and pressure are kept constant. Thank you.